So how do the halogens react? There's a halogen, okay? So the halogens react by gaining electrons. What we can do is we can balance this half equation to show how halogens react. We're going to make a Cl minus there because we need that extra electron to give that Cl a full outer shell. Remember, chlorine's in group 7 of the periodic table. I've got 2 here, therefore I need to put 2 there. And I've got a -2 charge on this side, so I need 2 electrons there. So we say that Cl2 has gained 2 electrons to make 2 Cl minus. And the key word there is gained. We know that reduction is gain of electrons. Reduction is gain of electrons. Therefore, Cl2 is reduced to Cl minus. And of course, this is only a half equation. There will be another half to that half equation to make a full equation, depending on what it's reacted with. We're just looking specifically at what happens to the chlorine here. Now, if you know that Cl2 is reduced, we know from topic 7 that we've just studied that the thing which is being reduced is the oxidizing agent. So we say that Cl2 is the oxidizing agent. So we can draw a conclusion from that. And our conclusion is that halogens are oxidizing agents. Okay, what is an oxidizing agent? Well, an oxidizing agent is something which gains electrons. In other words, oxidizing agents are reduced, and reduction is gain of electrons. Halogens are oxidizing agents because they oxidize something else by getting reduced themselves. Now, what we need to do is we need to look at the trend in oxidizing ability of the halogens. So we need to look at that then. Let's have a look to see what it's actually trying to do. We're trying to gain electrons here. Gaining electrons. Now, if you look at the size of atoms, so fluorine has quite a small atomic radius there. Chlorine is bigger. Bromine is bigger still. And iodine is even bigger. What we're trying to do here is, when we're oxidizing something with halogens, and this is a very simplistic explanation here, but the size here shows the trend. What we're doing is, we are gaining electrons. Now, because the electron that I'm going to be adding to this F atom here is going to be quite close to the nucleus, and there's not going to be many shells between that shell and the nucleus, so there's limited shielding there, then there'll be a very, very strong force of attraction when I'm trying to add that electron. However, if I come down here, because the electron I'm adding is going to be quite far away from the nucleus, it's going to be a very low electrostatic attraction between that electron that you've just added and the nucleus, and there's going to be loads of shells in here which are going to be shielding that electrostatic attraction between that electron and the nucleus. Then there's only going to be a smaller force of attraction between them. So therefore this process here is more likely to happen, okay? And this process here is less likely to happen. So what we can say is, we can say that F2, the top of the group here, is the most powerful oxidizing agent. What I want is an explanation of that. So F2 is the most powerful oxidizing agent because, so I'm going to give you some keywords here, and I want you to write an explanation of why that actually is. Perhaps compare F2 with something like I2. So here are the keywords. So gain, electrons, distance, shell, shielding, and electrostatic attraction. If you're not quite sure, maybe just rewind the lesson a little bit and listen carefully to my explanation here, in here, and when you're answering this question here. So I'd like to see a full paragraph here using those keywords. Please underline those keywords and tick them off as you've used them. And to be honest, if you can use those words correctly, you'll get full marks for that question. So we know that these halogens are oxidizing agents, and they do that by gaining electrons. And we can look at the evidence of that. We look at the evidence of that by displacement reactions. So displacement reactions give evidence of the oxidizing ability of the halogens. Okay, so let's have a look at an example here then. So if I've got Cl2, but I've got a solution of Cl2, so the everyday name of this would be called chlorine water, and I decide to react that with salt. Now this is what we call a sodium halide, remember? So this specifically is sodium bromide. So we've got a solution of chlorine and a solution of sodium bromide. We get a displacement reaction. And we have bromine water produced and sodium chloride solution produced. Now we need to balance that equation. We've got 2 bromines here, so we need 2 there. We've got 2 chlorines there, so we need 2 there, like that. Now let's have a look at the ionic equation for this particular reaction. Now it's been a while since we've done ionic equations, so what I'm going to do is I'm going to introduce them as if I would be doing GCSE, and I'll do one example like this, and then hopefully you get the idea, and then we'll go straight on to the ionic equation next time. So what I like to do is, I like to draw out what's happening here. So I've got Cl2 aqueous, right? So what's in there, in a beaker of Cl2 aqueous, is chlorine diatomic molecules with a covalent bond between those 2 chlorine atoms and molecules of water. So put molecules of water in there as well. And if we mix that beaker of chlorine water with a solution of sodium bromide. Now remember, this is a metal and this is a non-metal. Therefore this is an ionic compound, because ionic compounds contain a metal and a non-metal. So this is an ionic compound dissolved in water. So we've got Na plus ions and Br minus ions. We mix them together, perhaps in a bigger beaker. There we go. Now let's have a look at what we've made here. So we'll make bromine molecules dissolved in water. So let's put my water there. We make Na plus and Br minuses are going to turn into these 2 products here. So I've got NaCl this time. So that's Na plus and Cl minus. And I've got 2 of those. I can balance that equation there as well. And remember, I've got this dissolved in water. I've already got a water molecule there, but I'm just going to add another one there for completeness. Okay, so this is a representation of what's going on. Right, okay, now, what I've done here is I've just drawn the reaction. That's all I've done, just to try and visualise it. And now what we can do is we can have a look at what's changed and what hasn't changed. Let's first have a look to see what has not changed. Well, nothing's happened to the water. Nothing has happened to the water there. I'm just going to put very thin lines through that to show that they're just cancelling out there. Nothing's happening to the water. We can also see that nothing's happening to the sodium ions as well. We've got 2 sodium ions there floating around in solution, 2 sodium ions there floating around in solution. Everything else has changed. So it's changed because here we've got chlorine diatomic molecule, and we've broken that chemical bond there to produce 2 Cl- ions. Here we've got 2 Br- ions, and we've formed a chemical bond to make a bromine molecule. So what I can do is I can write down an ionic equation to represent what's going on here. So I've got Cl2 to start off with, which is here, plus 2 Br- makes Br2 and 2 Cl-. This is my ionic equation. Remember, an ionic equation does not include spectator ions. So in this case, my spectator ions are my Na pluses. So an ionic equation is often useful to see what's actually going on, and it draws our attention to the thing which is actually any chemical bonds and things which are actually reacting rather than the spectator ions themselves. So we need to have a look at why this reaction happens, and it gives us evidence of the oxidizing ability of the halogens. So I'm going to write down a rule, and we're going to write down a rule, and then we're going to use the rule to explain what's going on here. Okay, so here's our rule. A halogen can displace a halide in the solution if the halogen is more reactive than the halide in solution. Okay, bit of a tongue twister, but let's have a look. So we can see here that chlorine here is our halogen, and bromide here is our halide. Now, chlorine is more reactive than bromide. In other words, it's a stronger oxidizing agent. So this is more reactive, and that is less reactive. Because it's more reactive, it's able to displace the less reactive one away from the sodium ions to produce Br2. And that would only ever happen if the halogen is more reactive than the halide. Okay? Now, remember this is what we call a redox reaction. Redox reaction because it involves oxidation and reduction. So we can work out the oxidation state of the chlorine here. Remember, this is an element by itself. So the oxidation state is 0. Bromide here, the oxidation state is -1. Chloride, oxidation state is -1. Bromine here, the oxidation state is 0. So the chlorine goes from 0 to -1. So we're getting more negative there. If it's getting more negative, it must be gaining something which is negative. So it needs to gain electrons. Remember, reduction is gain of electrons. So the chlorine is being reduced to chloride. Here, however, the oxidation state is -1, and the product here is 0. So we're getting less negative. Something which is getting less negative is losing electrons. Remember, oxidation is loss of electrons. So we could write down that the bromide ions are oxidized to bromine ions. So we've got an ionic equation here, and we can pull apart this ionic equation to write down two half equations to show what happens to the chlorine, to show what happens to the bromide. Let's do the chlorine first. So you've got a Cl2 molecule here. Reduction is gain of electrons. We need to gain 2 electrons to make 2 Cl- ions. Let's look at the bromide. Now, this is oxidation. We're losing electrons here. 2 there. So I need to put a 2 here. Balance that with 2 electrons. That's oxidation. So the chlorine has been reduced to chloride. The bromide has been oxidized to bromine. Now, let's have a think about what's actually been oxidized. So the halide has been oxidized. Therefore, the thing which is doing the oxidizing is the halogen. So we write Cl2 has oxidized the bromide to make bromine and chloride. And that is because Cl2, or let's just write Cl. Cl is a better, stronger, you could use that word, oxidizing agent. It means it's more reactive than bromine. Okay? What we can do is we can use this principle to work out whether the reaction is going to happen or not. So let's pick a different reaction. Let's work out whether this is going to react. So we can see here I've got the halogen and the halide. Let's go back to our rule. Halogen can displace a halide in solution if the halogen is more reactive than the halide. So we need to work out whether that is more reactive than that. And it's not. It's actually less reactive. Remember, it's much bigger. So that electron that you're trying to add is much further away from the nucleus, and it's less attracted to the nucleus because it's further away and it's more shielded. Remember your explanation that you wrote down a few moments ago towards the start of the lesson. Here, okay? So there's no reaction. I want to explain why there's no reaction, okay? You can use some of those keywords to explain a little bit more detail rather than just copying the rule down. So I'd like to use some of those words there to explain why there's no reaction there. And what we can do is, if we do a whole series of experiments, we can actually predict which ones are going to react and which ones aren't. So we're going to draw like a little table here. So what I'm going to ask you to do is I'm going to ask you to do it 5 columns long, like this, 1, 2, 3, 4, 5, and then we'll do 5 columns up as well, 1, 2, 3, 4, 5. Okay, so this column here, I've just circled there, and that row there, we're going to put our start materials. Then our results are going to be in here, like that. So down here, I'm going to write down my halogens. Remember, halogens, they're diatomic molecules. So I've got beakers of these ready. And then I'm going to put my halides across here. Now, I'm only going to write down F minus, but that could be sodium fluoride, lithium fluoride, potassium fluoride. But remember, the metal there is only a spectator ion, so we don't need to write down the formula of the spectator ions, because this table, we're going to use that for any displacement reaction. Chloride, bromide, and iodide. So we're going to do 1, 2, 3, 4 times 1, 2, 3, 4, 16 hypothetical experiments. 16. And we're going to work out whether there's a reaction or not. So I'm going to put a tick if there's a reaction. I'm going to put a cross if there is no reaction. Now let's have a look at the ones that we've already done. So we know that there's going to be a reaction between chlorine and bromide, because chlorine is a better oxidizing agent than bromine. So chlorine and bromide, there's going to be a reaction. Tick. We know that there's going to be no reaction between iodine and bromide. Like that. And all we need to do, really, is just compare whether these are more reactive than these, essentially. That's all we need to do. Okay? Now, we know that fluorine is the most reactive. Now, we know fluorine cannot react with itself, so I'm not going to put a cross there, I'm just going to put a dash. Okay? And we know that chlorine can't really react with chloride, it's the same thing, and bromine can't react with bromide, and iodine can't react with iodide. So if you did that experiment, nothing would happen, but that's kind of obvious. But the ticks and the crosses, you've got to work out which ones will react or not. Now what you find is, you find that because fluorine is the most reactive, it's the strongest oxidizing agent, it can displace chloride, bromide and iodide, because fluorine is more reactive than all those three. However, if you look at chlorine here, chlorine is not as reactive as fluorine. Therefore, there's no reaction there. But it is more reactive than bromine, and it is more reactive than iodine. Let's look at this one then. Let's compare these two. Well, bromine isn't more reactive than fluorine, so there's no reaction there. It's not as reactive as chlorine either, but it is more reactive than iodine. Iodide isn't more reactive than fluorine. It is not more reactive than chlorine. It is not more reactive than iodine either, because it's the same thing, or bromine. So the only reactions that you get are these ones here. And they're the ones which follow our rule here. And we've explained that rule as well, and that trend. Okay?